All right, here we go. Chapter 2.2. Finally, this is going to give you a taste of calculus, right? This class is called pre-calculus, right? So we've been doing all the pre stuff, and here is kind of the calculus stuff. Calculus is built upon this idea of something called the limit, okay? And I'm going to show you what the limit is today. You kind of have an understanding of what a limit is, right? Anyone ever got a speeding ticket? Slow down. Slow it down. When you drive, when there's a speed limit posted, what does that mean? Go 50 over.
At least 5 if it's like.
A limit means to go past something, right?
A limit means it's the very top of what you should.
Very good, Brady. It is actually the opposite of that. A limit is something that you are not supposed to exceed.
You're not supposed to speed. It's just.
No, well, speed is relative. If you're going 30 and a 50, you're still speeding compared to a tortoise.
Oh, so if I'm going.
Speed is relative. Now, let's talk about speed limit. If the speed limit is 55, as it is on every interstate highway, right, as you well know, or at least it was in my day.
Minus Germany.
Quiet, Brady. When it's posted at 55, most people say we're supposed to drive 55, but that's just a limit, right? Can you actually drive 54? Would that be okay on the highway?
Yes.
Yeah, just stay in the right lane. Yeah, just stay in the right. Don't be going 50 miles an hour in the left lane. Left lane is for passing, right? We only have 2-lane interstates running across this great country, right? Right, and it's 55 everywhere. No, not really, right? I think Houston has, like right there around Katy, there's like, man, it's like 50 lanes almost, right? It's like one of the largest, widest. Yeah, it's like one of the widest highways in the world. Yes, sir, Brady. Thank you for raising your hand. Respect for your elders. That was fun. I had a good time.
1/3 of German highways do not have a set speed limit, so you can actively go as fast as you want on them.
Very good, very good. Did you know that 2/3 of American elevators don't have a weight limit? So you take your McDonald's on there, whatever, eat it on the way down. You probably go down pretty fast though, because you broke the cable, right? Anyway, it's hard to stay in character and not be in character at the same time. Limits are designed to have a boundary. It is something that you actually approach but do not exceed. That's the design, right? So we kind of say when the speed limit is 70 or even 85 when you get out past Kerrville on I-10. Most people say, hey, that is legal permission to drive 85. But really the limit is not necessarily something that even is attainable. So driving 84.5 miles per hour, that would be fine. Drive 84.999 miles per hour, that would be fine, okay? So do not exceed a limit. Limits are tied to this idea of continuity. We've kind of talked about this intuitive idea of continuity where if you could draw a function from left to right without lifting your pen or pencil, the function is continuous. But we're going to rigidly define what it means. And before we do that, we need to define what a limit is, okay? So take a look at this little function that I drew here on example 1. It's blue. It's got arrows going in both directions. I call it f of x, right? If you imagine drawing this from left to right, okay, like I did, you could draw it simply without lifting your pen or pencil, right? You could draw it continuously. There's no holes. There's no vertical asymptotes. And we talked about a jump as well, but we'll talk about that again later. Okay, so it is continuous. Now, let's take a look at x equals 3, right? I have it marked right there. If you go up at x equals 3, boom, you hit y equals 5, yes? So this value here, this dot right there, I'm going to make it bigger. This dot, we could say is f of 3, right? That's the function value. If you imagine this as a road and you're looking down from above, like you've strapped your drone to yourself and you're flying now, right? You're staring straight down. Could you stand at the 0.35?
Yes.
Yeah, you can. The function's defined there. So f of 3 is 5. This is the y value. This is the y value at x equals 3. It exists, right? You can stand right there like, hey, everybody, I'm standing at the 0.3 comma 5. And everyone's like, good for you. But there's another y value now that we are going to explore. And that y value is going to be what we call the limit. Okay, so let's do this. I'm going to switch to a nice color here. I'm going to make it a little bit bigger. Let's explore. Let's pretend that we're driving on this road, but we're watching it from above. As I drive along this road, on the left-hand side of 3, okay, and I start approaching 3 from the left-hand side. Here I am driving, right? I'm driving. As I get closer and closer and closer to x equals 3, not ever really saying I'm getting to 3, but as I get closer and closer and closer to 3, what are the y values of the graph getting closer and closer to? 0. 5. Does anyone else have another number besides 5 they would like? It's approaching 5. It's obvious, right? We're getting closer and closer to the dot, right? Okay. So like at 2.99999, what might be the value there? What might be the function value at 2.999? Not 4 point, because notice we're approaching from above, 5.001, right? So as we, and here's where the limit comes in. As we approach 3 from the left, our y values are approaching 5 from above. Would you agree? So the y values are actually getting smaller, aren't they?
Yes.
Now, as something continues to get smaller and smaller and smaller and smaller, it can go down to negative infinity, can it? I mean, just think about something getting smaller on the vertical plane. It can go down to negative infinity. This one's getting smaller and smaller and smaller, but it's not going down to negative infinity, is it? It's going down to 5. So 5 would be the lower bound or the limit that the y values can approach. Now, how close can you get to 3 from the left-hand side without actually getting there? 2.999, 999. Keep going, Brady. 999, 999, 999. Now, as soon as Brady stops, that's as close as we can get, right? No, someone else takes over for him. 999. Now we're closer, right? We can get infinitely close. We can get infinitely close to 3 from the left without ever getting there. Just like I told you, I can get infinitely close to that door without ever getting there, in theory, right? So as we get infinitely close to 3 from the left, our y values are decreasing. They're getting smaller, infinitely smaller, but not towards negative infinity, right? They're getting infinitely smaller, approaching 5, 5.00001, 5.00001, 5.00001, 5.00000. I'm out of breath, so I'm gonna take over. There's a good use of your voice. Keep going. Right, got it? So 5 is the limit from the left. 5 is the limit from the left. Here's how we write it. Here's how we write it. We write it like this: LIM. I write it in cursive. You can write it in print if you want. LIM is short for limit, okay? Underneath here, we're going to say as x approaches. That arrow means approaches. We're approaching 3. Now, to denote that we're approaching 3 from the left side of 3, we put kind of like a little negative ionic charge on the 3, okay? So the x approaching 3 from the left, that's what that means, goes directly under the limit. That's the notation, okay? Now, what we put in front of there, let me move this down a little bit. What we put in front of there on the same level now as the limit is the function itself, okay? So notice it's kind of the same as over here. I did f of 3. That's function notation. that defines the y value, f, and the input value, 3. They're both present. Input is 3, output is f of 3, okay? We have the same thing going on here. We have input and output present. Our input is 3. That's the value we're approaching, and the output is f. But we don't put the 3 in here. We write it like this. We read this as the limit as x approaches 3 from the left on the graph of f of x, or just of f of x. And then we put is, and what did we say that limiting value was? These y values are getting smaller and smaller and smaller and smaller and smaller, approaching 5. 5 is the limit. See that? Remember, the equal sign means is. So if you read it from right to left, 5 is the limit. Left to right, the limit is 5. Okay? So the limit is a y value. Got it? Fundamentally, at its very root, the limit, let me get a smaller, there we go. The limit is a y value. Just like the function value is a y value. But it's a y value that we approach, not the y value that we go stand at, okay? Now, sometimes they're the same, right? In this case, they are the same. This road is leading to this dot. Think of this dot as a bridge, if you will. Like there's like a chasm that runs through here. This road is connected to the bridge, okay? Let's look on the other side. Other side, okay? Let's say that we're on the other side, on the right side of 3, and we start driving back towards 3, okay? Look at that. As I approach 3 now from the right-hand side, that is as 3 gets smaller and smaller, and I can get infinitely close to 3 from the right-hand side, my y values are getting bigger now, aren't they? Okay, so at like 2.999, or I'm sorry, 3.001, the y value could be like 4.9. And then as it gets bigger, it could be 4.999, 4.9999999. So the y values are getting bigger and bigger and bigger forever and ever and ever. But they're not getting bigger going to positive infinity, are they? The limiting value is 5. So you can imagine how we would write that. We're going to write that like this: the limit, LIM, as x approaches 3 again, with a plus sign. The plus sign means from the right. It doesn't mean going right, from the right. So we're on the right-hand side. And then we define f, the function that we're driving on, essentially. So again, you have an input and an output. This is another y value. But it's the y value that we're approaching, not the y value we stand at. And what is that value, limiting value again? It's 5. Now, this is a very special case, because in this case, all 3 of these y values, the limit from the left, the function value, and the limit from the right, they're all the same. So if you imagine this as being a green road connected to a bridge, connected to a peach road, I don't know what color that is. Terracotta? Dark red. You can drive straight across, no problem, right? Road, bridge, road. That's very safe to drive through. Road, bridge, road. Road. Right, but we don't have a hole in this case. In this case, the road coming in from the left, which is the limit from the left, is connected to the bridge, which is the function value, which is connected to the road that goes out, which is the limit from the right. They're all 3 the same. So if you're driving your vehicle from left to right, you can safely drive straight through with no interruptions, no catastrophes, no discontinuities. Okay? Yeah. So we're going to define continuity now in terms of these 3 things: road, bridge, road. The limit from the left, function value, the limit from the right. They can all 3, believe it or not, exist independently of each other. Think of you have 3 different companies, right? And you're a horrible construction manager. You hire one company to build the road that comes in from the left. You hire another company to build the bridge. And then you hire another company to build the road that comes in from the right. And you don't tell them anywhere where they're supposed to build it, and they don't talk to each other. You can imagine them all building something and none of them connect, right?
Yes.
Yeah. And when that happens, we have a discontinuity. Okay. Or you might have one company builds the road coming in from the left, and the same company builds the road coming in from the right. You would imagine that that company would have the roads pointed at each other, right? But the company that builds the bridge never talks to them, and they build the bridge somewhere else. That could happen as well, right? Or you can have a company building the road that comes in from the left, and they also build the bridge. They're going to make them connect, right? Because it's the same company. But now you got some other company building the road from the right, and they're like, I don't like you guys. I'm not going to talk to you. And they build the road on the right somewhere else. So I want you to understand now that we have defined two new Y values that give us the power of analysis. We can now analyze what's happening now in the neighborhood of an X value, immediately to the left of 3 and immediately to the right of 3, without talking about what's actually happening at 3. It's a powerful tool of analysis, all right? And we call it the limit. So let's look at example 2. For the function below, analyze what's happening. Okay, so if you're looking at this as a construction project, you're looking at the roads from above, there's a chasm right here at x equals -4. The company that's in charge of building the road, they do it on both sides. It's the same company. They know where the roads are supposed to meet, right? So they build a road coming up to the edge of the chasm on one side. They build the road coming up to the same point on the other side of the canyon or the chasm, whatever. But the bridge company's like, nope, didn't get the memo. They build the bridge elsewhere. If you were driving, could you drive straight through x equals -4 on the road of f of x safely? No. Now, if you're Bowen Loop Duke, you might be able to make it across. Y'all know that analogy? The Dukes of Hazzard? Yeah. They were always jumping over chasms. And Roscoe P. Coltrane was like, yeah, you Duke boys. They always got away from the sheriff. Anyway. Evel Knievel. Yeah. Evel Knievel. Very good. Yeah, y'all know that guy. Oh, man, some video of him not landing safely. Just like a rag doll. Let's analyze it. Let's analyze it. Think of this as road, bridge, road. Okay. We have 3 tools now at our disposal. Road, bridge, road. Let's go ahead and say, what is the limit, LIM, as x approaches -4 from the left-hand side of f of x? Let's look at what f of -4 is, and then let's look at the limit as x approaches -4 from the right side of f of x. Get this notation down. Memorize the limit notation, because you know how important notation is to me. If you don't have it right, you're going to lose points. These are your 3 analysis points. If you want to label them just to kind of make it easier for yourself to remember, the limit from the left, is always the road coming in. The function value is always the bridge. And then the limit from the right is always the road that goes out. When we analyze it coming in from the right-hand side. But if you were drawing from left to right, it would be the road going out. So I just wrote those down. Now, instead of putting an equal sign and going left to right, I'm just going to work straight down. We know how to do that. All right, let's analyze. What do you think the limit from the left is? Hop on the road somewhere to the left of -4. How far to the left of -4 do you want to jump on the road? You want to jump on it over here? That's way too far. No, just hop on the road like immediately to the left. You can hop on right here. Start heading back towards it. What am I getting closer and closer to? As x approaches -4 from the left, my y values are getting closer and closer and closer and closer to what y value? 2. 2, right? We're getting right up there on the edge of that open circle, which happens to be at y equals 2. Now, what is f of -4? Is it also 2? When I ask you for the function value, that's looking up and down for where the graph is. Where is the bridge? It's at 3. It's up at 3. Thank you. Okay. You haven't seen this yet because this would come by way of some crappy construction project, but mathematically we would call it a piecewise function. And that was at the end of 2.1 and we skipped it, but we'll get back to it. Okay, so everyone okay with this? This is really important. The road coming in from the left, the y values are getting closer and closer to 2. Where do we stand when we go to -4? Well, we have to stand on the point, and the point is up there at 3. They built the bridge in the wrong place. What would be the limit as we approach for -4 from the right? Well, hop on somewhere to the right, start heading back. You get closer and closer and closer to what y value? 2. Okay. So notice then that before today, you only had the power of talking about function values. Where is the y value at a certain point? Right? Now we have another tool. We can analyze what's happening in the neighborhood of that point. All right. Would this be continuous? Obviously, could we drive straight across? No. What type of discontinuity is this, do you think? It's a hole. Yeah. And what is the formal proper name for a hole? Oh man, it's so beautiful. You put it on a test one time and everybody knows what it is now. It's a removable point discontinuity. And remember, the reason we call it that is because we can go kick Swiper's butt, use my cane to get that point back. And all I got to do to make this thing continuous, let's say I got the point now in my hand, is put it down here, right? Just pick up that bridge and move it to -4, 2, and now it's continuous, right? And then we go home with as a job well done, and then overnight, Swiper takes, dang Swiper. Don't hire Swiper to build your bridge, okay? That's what makes it a removable point discontinuity. You can simply redefine the function at that x value and make it continuous there. This is the only type of discontinuity we study that is removable. The others are non-removable. There's no way to put a bridge down at one point and make things connect. This is the only one, okay? It's a single point discontinuity. All right, that's kind of important. I want to look at something here. The roads are lining up, yes? That's really important. That's really important. Anytime you have a hole, whether the bridge is built somewhere else or there's no bridge built at all. On the test that we just took, there was no bridge at all. If there was a hole, there was no bridge, but the roads would still line up. Anytime you have a removable point discontinuity, the roads are going to line up, whether or not there's a bridge or not. Here's a new little theorem here, okay? The limit as x approaches, or we'll just use this one here, -4 of f of x. What's different about this limit from the ones I've written previously?
There's no negative or positive.
Yeah, there's no left or right. There's no negative or positive ionic charge, right? We call this the general limit, not the general Lee. That's what the Duke boys drove. This is the general limit. Okay. And it is going to equal the same y value to, as long as we're going to put if and only if. It's a double-headed arrow. That's not a really good double-headed arrow. If and only if, IFF is another way to say that. If and only if the limit as x approaches -4 from the left of f of x equals 2, bless you, which equals, bless you, the limit as x goes to -4 from the right of f of x. Okay, in other words, the general limit only exists if the two one-sided limits are the same. If the roads are pointing towards each other, then we can say the general limit exists. And if the two roads on either side are not pointing towards each other, or they don't exist, then neither does the general limit. Okay, so the double-headed arrow just means you can put an if on either side. If the general limit is 2, then we know that the two one-sided limits are both 2. And then the other way around, if we know the two one-sided limits are 2, then we know the general limit is also 2. Okay, this only talks about the roads. In the analogy, this is only a discussion about the roads. Okay, and it's about the roads lining up. If you want to write that in there, it has nothing to do with the bridge. It has nothing to do with the function value. Okay, the general limit will only exist when the roads line up. So can we say on this example that the general limit is 2? Yeah, okay. So the limit as x approaches -4, in general, no plus or minus ionic charge of f of x is 2. Okay. Actually, if you had to write the reason, it would be since 2 equals 2. That would be the reason. Which 2 are we talking about? Those 2 down below. The roads are pointing towards each other, so the general limit exists. These are parentheses, best friends. Good fishing buddy, those parentheses. Damn seagulls. Does the general limit exist on example 1?
Yes. No. Yes. 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 Yes.
Here's the question you got to ask yourself. Do the roads line up with each other?
Yes. Yes. Yes.
We already said on example 1 that we could drive safely across, right?
Yes.
Therefore, the roads have to be lining up. Yeah. Thanks for the comic relief, Mr. Vance. Yeah. No, but yes, the roads are lining up. So, or actually, let's do it the other way around. Okay. Let's look at this 5 here. That's the road coming in from the left. And let's look at this side. That's the road coming in from the right. Okay. Since 5 equals 5, and we're talking about those, comma, we could say that the limit as x approaches back here, it was 3 in general, no plus or minus of f of x also equals 5. Okay. We have now seen 2 examples where the general limit exists. These are the only 2 cases where the general limit exists, because these are the only 2 possibilities for the roads to line up, right? The roads have to line up for the general limit to exist. What's the only other option then at that point? There's either a bridge connecting them, or there's what? Not a bridge connecting them. Not a bridge connecting them. I don't care if the bridge exists or not, but the bridge, if it does exist, is not connecting them, right? Okay. The bridge can exist independently. These are the only 2 cases, all right? Let's just go ahead and say this, because it's good to write things down, right? Like take meds at 12, take meds at 1, take meds at 2. Meds, right? When you call them meds that are prescribed by doctors, you don't call them drugs, right? Take drugs at 1, the high wears off. Take more drugs at 2. That's not what we're saying, right? We're calling them meds. My blood pressure is rising. Take more meds, right? The general limit. The general limit only exists if the roads, which are the 2 one-sided limits, right, line up. Okay, and here's the first case. Continuous. And the second case would be what? Whole. That's it. Those are the only 2 places. Now, when I did the whole example, I didn't even put a bridge, because you know why? It doesn't matter. It doesn't matter for the roads. The roads don't give a darn about the bridge, because you know what? They're concerned with being the best dang roads they possibly can. All right. So far, so good? The limit. Man, you didn't even know about a limit before you woke up this morning. Oh, by the way, waking up this morning and making it to school. I don't know if you heard, but Comal ISD was going to have a 2-hour delay on the start of the day because, you know, they have a lot of flooding out in those parts out there. But then they ended up canceling school for the entire day. Comal ISD is canceled today. So we are now one day smarter than what? All Comal ISD. Now, would you say that we're one day smarter than them or one day smarter than they? One day smarter than they. That's the correct way to say it. Let's say it together now. We are one day smarter than they. That's good. It sounds awkward to end with they, although it is perfectly acceptable. To make it sound better, we add another verb at the end, are. We are one day smarter than they are smart, right? We don't even say smart, but that's the sentence structure. When you say we are one day smarter than them, that is totally incorrect. You might as well say we is one day smarter than them is.
Yeah.
So learn to speak correctly. The true test when you speak like that is to say are at the end. We are one day smarter than them are, or we are one day smarter than they are. Oh, that's the way. And then to sound pompous and arrogant, you can just get rid of the are. We are one day smarter than they. Right? And that's okay. You can stop there. You can stop there. Right? We learned something today now, right? Grammar. Grammar, the rules of grammar and the rules of math.
Yes.
Two sides of the same coin. Two sides of the same coin, right? You dangle a participle over here. You don't distribute a negative over here. Either way, you're miscommunicating. You whippersnappers need to get that straight.
We're so smart.
One day smarter than they are. Yeah. All right. Let's look at example 3. We've seen a discontinuity like this in the previous section.
Yes.
Just look at this function f of x at x equals 1. Just intuitively, would you say that this function is or is not continuous at x equals 1?
I would say it's not.
It would be not. Good. Safely. The goal to be continuous is, can we drive across safely with hands on the wheel at 10 and 2, not exceeding the speed limit, actually going 20 miles below the speed limit in the right-hand lane, right? Eyes looking out between the dashboard and the steering wheel, out the windshield, right? Safely driving across. That's the litmus test. We can't do that here, okay? But let's go ahead and analyze. Let's set up our 3 tools of analysis, yeah? I'm tired of using red. I'm going to use dark red. The limit as x approaches 1 from the left of f of x. F of 1, and then the limit as x approaches 1 from the right of f of x. Remember that on each of these 3 y values now, you need to show your input, that's your x value, and you need to show your output, that's the function value. Both notations, limit and function, contain both elements, right? The limit is a little bit cumbersome, but that's okay. You can get used to it. If you just write the limit as x goes to 1 from the left and you don't put the f of x there, is that correct? No, because you are not defining the road, right? The road is the function. And if you don't know where you're going, I guess any road will take you there, right? Good luck, loser. I mean, loster. You're lost, probably. Losers. All right. So you need the f of x. That would be like, instead of saying f of 1, you just said of 1. That doesn't make any sense at all. Where's the function, right? They both have f and they both have the x value. Now, let's go ahead and write the values directly underneath there. I'm going to go with purple nurple here. As we approach, no, purple doesn't contrast well enough. Let's use the cool yellow one.
The gold one, bottom right. Bottom left, I mean.
Bottom
Go right,
left.
Go right, go right.
Are you colorblind?
Bottom left.
Oh, that's like, that's pea green, whatever. Call it piss green back in the day. What? No, when we say pea green, we mean like the vegetable. If your pea is green, you need to go see a doctor. The limit as x approaches 1 from the left is what? Come on, help me, everybody. What are we getting closer and closer and closer to? What y value? -3. Very good. What is f of 1? Now, when I say f of 1, I mean go stand at 1 if you can. Stand on the dot, right? It's like a marker on the floor. Go stand there. Go stand on the bridge. What's the y value of the bridge? -3. Okay. So far so good. 2 of the 3 things are met. If we're trying to drive across safely. We've driven on the road coming in from the left. Hey, it's connected to the bridge. We're driving across the bridge. We get to the end of the bridge and what? Damn seagulls. You drive off, right? You stop, you turn around, you go back, and you're like, what the? No, we're not the Duke boys. What would be the limit from the right-hand side?
Generally negative.
Well, what would be the y value? -5. See that? As we approach 1 from the right-hand side of 1, infinitely closer, we'll get closer and closer to -5. Here's the litmus test now. Now that we've quantified all 3 of those, you just compare those 3 numbers. Are they the same? No. Therefore, the function is not continuous. We have established now rigid criteria for determining if a function is or is not continuous at a point. You met the limit today. That's awesome. Y'all have a great rest of your day, you whippersnappers.